Hi everyone, I'm going to be talking about classifying spoken location names. My name is Jyotika Singh and I work as a Director of Data Science at i6 Media, which is a content and audience intelligence company based in Washington, D.C. I've listed my social media handles here and I'll be posting this slide deck after the conference on Twitter. So if anybody wants to look at it for reference, you'll find it there. I've also linked my GitHub account here, specifically this one project that contains a lot of functionality, feature building, and machine learning models building capabilities from audio signals. It's called PyOhio processing. Let's consider two locations that sound a little bit similar and read a little bit similar. So they both have two syllables. One is London, one is Boston. The plots you see underneath are just a time domain representation of somebody speaking London on the left and Boston on the right. So we see they're similar and the words are similar. I want to see if we can differentiate between these two spoken location names. Now, if you look at these plots, they do look different. So one may think that temporal features or the time domain signal representation here should give us enough to build a model that is able to discern between the two location names. However, if you look at this slide, every plot that you see on the left is London and everything you see on the right is actually spoken representations of Boston. And now you see every plot looks so different, and it is because people have very different ways of saying the same name, different accents, different styles, and all of that represents and makes the signal look very different in terms of the time domain representation. Before actually building the model, let's talk about what is an audio signal, how we can build the model, and what useful information we can extract from the audio that can help us build these models, and the tools in Python that can be leveraged. Before diving into audio, I want to talk about what machine learning is at a high level. There are three stages: data, training, and evaluation. In the data stage, apart from data collection and cleaning, data transformation plays a major role in converting your raw data into features, which can then be used to train machine learning models. There are different feature generation methods suitable for different types of data. As you may know, that word-to-vector is a very great popular feature representation for a text corpus, but if we pass in an audio signal or just numbers, the representation that we're going to get is not going to be very meaningful. So we will be talking about the useful feature generation methods specific to audio signals. An audio signal is essentially something that vibrates in the audible frequency range that our ears are tuned to perceive. There are many great MATLAB tools that have a lot of functionality to do audio feature processing, but Python is picking up as well with time. Two important terms to know about for audio signal processing is spectrum and cepstrum. Spectrum is nothing but the frequency domain representation of an audio signal, and cepstrum results from taking log magnitude of the spectrum followed by inverse Fourier transform. Spectrum and cepstrum both convey a good deal of information about the audio, and very good features can be derived from both of them. The reason we care about the frequency domain of an audio signal is inspired by the way human hearing works. There is a fluid-filled spiral-shaped structure called cochlea, which has thousands of tiny hairs, and each hair is connected to a nerve. Some hair are longer in length and some are shorter, and they resonate with different frequencies of sounds. And thus our ear is considered to be a natural Fourier transform analyzer. We'll now talk about some audio features that are derived from the cepstrum of the audio, and we'll see it finds a lot of use in our location name classification task as well. The Mel frequency cepstral coefficients, also called MFCC, are constructed by passing the spectrum of the audio signal through the Mel scale filter bank, followed by log magnitude and discrete cosine transform. The shape of the filter looks very much like the rectangles that you can see on the slide, and the inspiration really comes from how the human ear perceives audio. Another very useful filter bank that is used to construct audio features is called the gamma tone filter bank, and it looks similar to the MEL filter bank except for the peaks are much softer in this filter bank. And this is what is used as the front end simulation of the cochlea. So this again tries to even more closely represent how the human ears perceive sound. The spectrum of the signal when passed through the gamma tone filter bank followed by downsampling for loudness compression, and the discrete cosine transform results in GFCC features, which is the gamma tone frequency cepstral coefficients. In both cases, for MFCC and GFCC, we notice we are taking a discrete cosine transform, and the reason is this transform is known to essentially capture the very peaks and an overall shape of the signal. So like the bigger peaks and the overall shape. It is known that the smaller variations in the signal at that point is nothing but noise. So we do want to capture that high level shape of the signal, and that contains a lot of useful information about the audio itself. Here's the plot of an MFCC of a speech signal versus a GFCC of a speech signal, and we see both these coefficients definitely convey different types of information for a same audio signal. Listing out for everybody's reference some other features that are useful in building audio classification models. The good thing is that you don't really have to remember how some features are constructed. It's mainly for context. They're great tools that help with getting this feature from a raw audio in Python. This particular slide lists out all the tools that are extremely popular and are used widely in Python and are very helpful in getting features, visualizations, and a lot of other things that you may want to do with audio signal. With all that information now, let's get back to building our location classifier that discerns between spoken, London, and Boston audios. Let's consider a task where we are only given female voice samples to train our model on, and then we have to test it on male voice samples. So in this case, we have 23 samples for London and 23 samples for Boston, and they're all in female voice. And we are testing on 17 samples for each of the classes on male voice. We first try the MFCC feature, and we train the model, and that's the confusion matrix that we see on the left side. So the confusion matrix looks decent and it looks like it's doing good for the most of it. But when we test on the MFCC generated model, we see we are only getting 8 out of 17 correctly classifications for London and 9 out of 17 for Boston. So we're seeing it's not doing that well on the testing data. When we change our feature from MFCC to GFCC, now we see the confusion matrix also looks better on the training data, and the testing results look better as well, with 13 out of 17 correctly classified for London and 13 out of 17 correctly classified for Boston. Further adding features related to the spectrum of the signal. So spectral features and GFCC features combined in the same model results in an even better training results, a training confusion matrix, and even better results for the test set, with 15 out of 17 correctly classified for London and 14 out of 17 for Boston. In this entire effort, we are keeping the classifier constant as the SVM classifier. And if one were to experiment further with the classifier itself, the model would improve further and can be tuned beyond just playing with the features. But the effort here is to show the capability of the different features and what works best with data of this nature. Extending on the exercise from the previous slide, now we are still using audio samples for spoken location names of London and Boston, but now we are making our training data more representative of what we are expecting in the testing samples. So now we still have 23 samples each for London and Boston, but the samples are between mixed male and female voices. We tested out on first MFCC features, and we see now we are able to correctly classify from the testing data 9 out of 17 samples for London and 14 out of 17 for Boston. So these numbers definitely look better from what we saw previously when our training data set only contained female models. Now that our training data set is more representative, we see model improvements and we see the feature MFCC doing better itself for the entire model. Same thing if we go to GFCC feature and then add spectral features on top of that, we see further improvement as it is classifying 15 out of 17 samples for London and then 14 out of 17 for Boston. The classification backend is kept constant as SVM, and this entire analysis has been performed using PyOhio processing, where we're able to extract the different features of users choosing and the different classifier models that we want from the scikit-learn offerings. And then all the visualizations that I have performed is using matplotlib. Here's a resources slide. I wanted to list out everything that I've spoken about or used. And thank you very much, everyone, for tuning in. Have a wonderful day.